Mesdames et messieurs, bonsoir.
Good evening, ladies and gentlemen. Welcome to all those who are here on Monday and Tuesday evenings and who come back to join us this evening for this third lecture on the 19th Right Colloquium. The subject today, well, you know, is a conference which should have been live. In fact, the auditorium has a space for 600, and there are hundreds more following us on their screens. And I'm sure that there are going to be even more this evening. My name is Olivier Thibault. I'm a journalist and a director of scientific communication for the Geneva Science and Diplomacy Foundation. I'm very happy to be in charge of the presentations this evening. As you know, every year we have a privilege to welcome at the University of Geneva speakers of great renown. This year is not an exception. We've got a whole range of mathematicians, incidentally, who, with their presentations, with their lectures, may remind you of what it was like being back at school. And these persons are involved in fascinating academic research, dealing with very specific things, because mathematics is not just a toolbox for sciences or the other sciences. Research areas are vast fields. It's something that's very lively, which go well beyond the academic field. And you'll see their applications in industry and finance. And it also helps us to explain the world. Galileo at the time, who said, and I'll quote him, "You can only understand the universe if you understand the language and the characters in which that language is written. Nature is described in a mathematical manner." And you will see that the lecture this evening is very much in line with this adage. Now, this evening is going to take place in two parts. First of all, the lecture, then there will be a question and answer session. It will be done online, and I will explain this to you in a few moments. Let me give the floor to the president of the Right Foundation. It is under their patronage that this conference is taking place, and it is a foundation which really promotes dialogue between science and society. Thank you. Ladies and gentlemen, good evening. The Right Foundation is very happy to welcome you once again this evening, and I'm sure that you're comfortably seated in front of your screens at home, and we hope that you're going to really follow something which is of great cultural importance. Since the beginning of this week, we've seen how mathematics and other spheres of life are able to cross-fertilize, how we are able to understand nature, and physics in particular, by having mathematical tools which are necessary to decode them, and how nature allows us to develop our intelligence. For example, how sometimes the result of mind games without any physical representation are at the center of the description of large swathes of nature. I think it is also fascinating to see how very simple models, far from physical complexities, may suddenly show how subtle they may be and rich in teachings. So we're going to continue in that vein this evening, listening to Martin Herrère, who is going to be talking about the smallest elements which are accessible by physics, and at the other end of the scale, what is limited by space. And I'm sure that we're all going to have a very lively and interesting evening, and I look forward to hearing him.
Merci, Thierry Courvoisier.
Thank you very much, Thierry Courvoisier. Now, we were saying that this is going to be as interactive a session as possible in spite of the conditions. So you have the possibility to ask questions to the speaker of this evening. You can do so online. So those of you who are following us on the Colloquium's site, there is a little white box. Please insert your question in that box. And those who are following us on Facebook Live, please also go to the Colloquium site and ask your question. You can do this in French or in English. We are fortunate enough to have an interpretation at this conference in English and in French. In fact, if you want to follow the conference in English, there is a button that you can press so that you can switch to the English language. And the interpreters are with us here, allowing us to translate this series of conferences into English. So, Our speaker this evening. Now, you've probably seen his name in the media. He got a new science prize, the Breakthrough Prize. He won a few weeks ago, which have been added to others. He won the Fields Medal. He won that prize in 2014, which is the Nobel Prize for mathematics, if you want to make an analogy. Mathematicians consider that this is their Nobel Prize. Martin Heyer is the most Genovese of all the speakers this year because he did most of his studies here. And I'm going to ask somebody who also taught here in Geneva and who knows him very well. And I'm just going to ask Jean-Pierre Achman, who is honorary president of the mathematics here in Geneva, to come and introduce Sir Martin Heyer. Thank you and good evening. Now, you've already heard the prizes that Mr. Heyer has won, and I'm sure you've also heard that certain Martin Heyer has not only won the Fields Medal, but he also won some very important other medals. But perhaps what is less known about him is that since his birth he's been a citizen of Geneva, although he actually carries an Austrian passport. So, I'm going to go rapidly through the period of time he spent in Geneva. His father lent me a few photographs which I want to share with you. He was born on the 14th of November 1975 at the Bois Gentil Clinic for the Genevese amongst you in the audience, and his parents lived in Verrières on the outskirts of the city. You can see his mother with him, and you can see him against the Salève mountain with his brother and his sister. He was the eldest of the three. Now, I wanted to show you that he had a lot of hair at the beginning when he was a child. Now he doesn't have so much hair. He did all his schooling in Geneva. He went to the pre-secondary school and he went to Claparède secondary school. As his father was professor of mathematics at the University of Geneva, he became interested himself very early in mathematics. This is in Seoul, where he received the Nobel Prize. You can see his father on the right-hand side, Ernst Heyer, and Soumei Li, his wife. I will show you how he became interested in mathematics. I hope it's legible. At the primary school, he says, I want to be a mathematician when I go to university. I want to be a mathematician because I am really interested in this subject. My father, who is a professor of mathematics, taught me 3 years ago how you could draw a curve based on a simple formula. A bit later, at my request, he explained to me how the sinus functions. And then 6 months ago, or 6 months later, I should say, he taught me how he started to get interested in statistical calculation. And I observed the signification of several signs which refer to statistics which were completely obscure to me until then. And as Hugo was saying, some things are or seem obscure in mathematics. However, I wanted to continue my studies in secondary school, and later I wanted to continue mathematics at university level. But there is another aspect of Martin Heyer's background which is perhaps a little less known. He participated in the Schweizer Jugendforsch, which is Swiss Youth Researchers. He participated in this on 3 occasions, and he produced a program which is called Amadeus, which analyzes sounds For copyright reasons, I didn't enlarge the picture too much, or the advert for the program, but you can find it on the web. In any case, it's a major commercial success. Martin then carried on to do his studies at the University of Geneva, as you've heard. He studied theoretical physics, but apparently this type of education was sufficiently advanced to transform into a more than respectable mathematician. And as is well known, he won the Fields Medal in 2014, and he celebrated this win with his parents. And it is mother who produced a large cake with a Fields Medal in marzipan to decorate the cake. But he also celebrated with all those who studied with him. You can see the team behind him or next to him. Let me just also point out, in finishing this introduction, that around the table there was John Jones, who also started his studies and who is shown in the cafeteria and who's no longer with us. So I hope that you will enjoy the trip of the infinitely small to the infinitely large with Professor Hira.
Merci beaucoup.
Well, thank you very much.
Merci Jean-Pierre pour l'introduction.
Thank you, Jean-Pierre, for having introduced me.
Bon, j'aimerais commencer par dire que c'est un grand
And
plaisir
let me start by saying that
presque de retour
I'm
à
very
Genève
happy
ce soir,
to
en tout cas
be back in
virtuellement.
Geneva, at least virtually.
Et j'aimerais commencer aussi par remercier les
And I
organisateurs du
also like
colloque,
to
en
thank the
particulier
organizers of this colloque, and in particular Thierry
pour
Courvoisier,
l'organisation
Mr.
scientifique.
Alexeyev from the scientific board.
Pour la conférence de ce soir,
For tonight's
j'aimerais
conference,
commencer par vous montrer
I'd like to start
un petit
with
film.
showing you a
Donc c'est une
short
vidéo qui a été
video
réalisée par un astrophysicien australien
which was made by
qui s'appelle
an
Daniel
Australian
Obreshkov.
astrophysicist.
Dans cette vidéo,
His name is Daniil
on
Obreshkov.
part de l'échelle sous-atomique. Donc ce que vous voyez
In this
ici,
video,
ça
you start
c'est
with the
censé représenter
subatomic scale. What you see
des
here
protons et
is
neutrons
supposed
à
to
l'intérieur
show
du noyau
protons
d'un
and
atome.
neutrons
Et,
within
les
the
petits
nucleus
bouts
of an
coloriés,
atom, and what you
c'est
see
censé
in
représenter
colors
des quarks.
is supposed to represent quarks.
Et maintenant, on zoome.
And then you can
Et
zoom out.
toutes les 3 secondes,
And every 3
on
seconds,
multiplie
you
l'échelle par un
multiply the
facteur
scale
10.
by a factor of
Vous voyez,
10.
maintenant, après quelques secondes,
So
on
after a
voit
few
l'atome
seconds,
entier. Donc
you
ce
see the
nuage-là,
whole
c'est
of
le
the
nuage
atom.
d'électrons.
This cloud is the cloud of
Ensuite, quelques
electrons.
secondes plus
And then
tard,
a few seconds
on arrive à
later,
l'échelle des molécules.
you reach
Donc
the
ici, on se
scale
trouve
of
dans une molécule
molecules. This
d'ADN.
is a DNA
On voit que cette
molecule.
molécule
You see
d'ADN est
this
à l'intérieur d'une
DNA
cellule.
molecule is
Ici, on
within
voit
a
le
cell.
noyau de la cellule.
Then
On
you
voit que c'est une
see
cellule
the
blanche
nucleus of the cell. You see this is a white
qu'on
cell,
voit à l'intérieur d'un
which you
capillaire
can see
sanguin
within
et dans
a
l'œil
blood
d'une
vessel.
personne.
in
Ici, on
the
est arrivé
eye of a
maintenant à l'échelle
person.
du centimètre.
So you reach the scale of a
maintenant,
centimeter, then
Donc là,
the
on
scale
arrive
of a
aux échelles
meter.
habituelles que vous
This is the
connaissez.
usual
On continue à
scale
zoomer.
which everybody knows, but you go
Et,
on zooming
On
out,
arrive très
and
rapidement
very rapidly
à l'échelle d'un pays.
you reach the scale
Ici,
of a
on
whole
arrive à l'échelle
country.
du kilomètre.
This is the
déjà
scale
de
of
la
1
dizaine, de la
kilometer,
centaine
then
de
10
kilomètres.
kilometers, 100
Bientôt, on
kilometers.
voit la Terre tout
and
entière.
Soon you
Puis
see
environ un
the
millier
whole
de
Earth
kilomètres, quelques
appear,
milliers de kilomètres de diamètre.
several thousands of kilometers, then
Et là, on voit l'orbite de la
many
Lune,
thousands of kilometers, the
On
orbit
arrive très
of
vite
the
la
moon,
taille des planètes intérieures du
size
système
of
solaire, on voit
planets
les autres
of
planètes
the
intérieures.
solar system, the
On
other
voit la
planets,
ceinture
then
d'astéroïdes,
the
maintenant les planètes extérieures.
belt of asteroids.
Encore quelques secondes plus tard,
A few
on
seconds
voit
later,
maintenant le système solaire
you see the
entier,
whole
avec,
solar system
tous les astéroïdes
with all
externes.
the
Et là, on voit
external
les étoiles les plus
asteroids,
proches.
the closest stars.
On arrive dans l'amas d'étoiles dans lequel on se trouve. Là, on commence à voir
The
la
mass of
galaxie, la Voie
stars
lactée.
where we are,
Donc là, on est
and
déjà
the
à des
Milky
centaines de
Way.
milliers d'années-lumière en taille. tout ça en quelques secondes.
Thousands of light years
Là, on voit
away
déjà
from
des amas
us,
de galaxies, et finalement,
and all that
ici,
within a few seconds. Then
à l'échelle du
these
milliard
masses of
d'années-lumière,
galaxies, and at the scale of
on
1
arrive à
billion
l'échelle de
light
l'univers
years,
tout entier,
this is the whole of the
avec des amas de
universe
galaxies énormes.
with huge masses of galaxies.
De cette vidéo, j'aimerais retenir deux choses. Donc la
What
première
you
chose
could
que j'aimerais
keep
qu'on
in
remarque,
mind after seeing this
c'est
video is that
la notation qu'on
the
utilise
way we
pour
use
représenter les
to
nombres,
write down
vous avez tous appris à
numbers
l'école la notation scientifique avec les
is
puissances de
taught
10.
at school
Cette
with
notation est
powers of 10,
extrêmement puissante. Elle nous permet
and this
de
enables
représenter des
us
nombres
to
énormes
show
très
huge
facilement. Donc, vous avez vu
numbers.
dans cette vidéo,
As you've seen in this
nous sommes
video,
partis de l'échelle la
we
plus
started
petite qu'on
from
puisse
the
imaginer,
smallest
celle
possible
des particules
scale,
sous-atomiques,
the scale of
et
subatomic
pour arriver à l'échelle
particles.
la plus grande qu'on
And
puisse
then we
imaginer, celle
ended
de
up
l'univers
with a
tout entier.
huge
Ça nous a juste pris 2 minutes.
scale of the
Et donc,
whole
c'était une
universe
quarantaine
within 2
d'échelles de
minutes.
grandeur.
That
On
means
arrivait de
about
10 puissance moins 15
40
mètres
scales
particules
of
élémentaires,
magnitude,
à environ 10 puissance
from
25 mètres.
10 to the
la
minus
taille de l'univers.
15 to 10 to
Si
the
on prend,
40th
on pourrait faire la même
or
chose
41.
avec des échelles temporelles.
If you
Si on
did the
mesure
same
l'âge de
with
l'univers en
time,
termes des
and
échelles
you
de temps
wanted
les
to
plus
measure
courtes,
the
on
age
peut
of the
imaginer qui
universe
seraient les
from
vibrations
the
atomiques.
smallest
L'âge
possible
de
scales,
l'univers est environ
in other
10
words,
puissance 30 et
atomic
quelques, 33,
vibrations,
34,
you'd reach
en
about
vibrations atomiques.
10 to the
Si on
40th or
multiplie tout ça,
33,
donc imaginons qu'on découpe l'univers,
and you
l'histoire
could
de
cut
l'univers
up
tout
the
entier.
story
Donc,
of the
l'univers tout
universe,
entier,
the whole of the
on le découpe
universe,
en
and
petites
you
cellules de
cut
la
it,
taille
if you
d'une
cut it
particule
out
élémentaire,
in
et on regarde
particles,
tous les instants de
you
temps
would be able to
possibles
see
de
all
cette
the
cellule.
instants of
On
time.
arrive à ça à environ 10 puissance 150.
That would lead you up
instant,
to 10
disons,
to
dans
the
l'espace-temps de l'univers tout entier, de
150th
sa naissance jusqu'à l'instant
for all
présent.
the instants
Donc,
of the universe
à
from
toute
its
fin
beginning
utile,
to now.
Qu'est-ce que ça nous dit? Ça nous dit qu'un nombre comme 10 puissance 150,
This
qui est
means,
très
in other
facile à
words, that
écrire,
10 to the power
est déjà infini à
150
toute fin
is
pratique.
already more or
Parce que
less
si on prend
infinite
la chose la plus
for all
petite
practical
imaginable
purposes.
dans l'univers,
Because if you take
et
the
qu'on
smallest
l'utilise pour
possible
mesurer
thing
la
in the
chose la
universe
plus
and you
grande
use it to
imaginable,
measure the
on
biggest
arrive à
possible
environ 10
thing,
puissance
you
10
reach
puissance
a
150.
level of about 10 to the 150.
Donc, juste pour illustrer sur cette taille,
To give you an idea of
vous avez
the
probablement
scale of
tous
magnitude,
entendu
you probably all
parler une
heard
fois du
about
paradoxe du singe savant.
the paradox of the
C'est le
clever
paradoxe
monkey,
suivant qui dit que si on prend un
which
singe
says that if you
qui
have
tape
a
de
monkey
manière aléatoire sur une machine
typing on
d'écrire,
a typewriter
si
more or
on
less
attend
at
suffisamment
random
longtemps,
and you
finalement, il
wait
va taper les œuvres
sufficiently
complètes
long,
de Shakespeare.
that monkey
Et,
will be able
typiquement,
to
le
type
paradoxe est
in
résolu
the
en
whole
disant,
of
ah oui, mais
Shakespeare's
évidemment,
work.
on ne verra jamais ça,
Of course,
parce que
this
ça
can
prendrait plus
never
longtemps que
happen
l'âge de l'univers.
because it would last
Mais en fait,
longer or take
dire ça,
longer
ça rend pas
than
du
the
tout
whole
justice,
age of the universe.
à
Well,
la
that is
différence
not quite
d'échelle
true because
énorme
the difference in
qu'il faudrait.
scale is absolutely
Si on se
huge.
contente pas des œuvres complètes de Shakespeare, mais juste
If
d'une
you just
page de Shakespeare.
Concentrate on one
Donc,
page
juste
by
pour que le singe
Shakespeare.
tape une page de
For the
Shakespeare,
monkey to
il
be
faudrait
able
qu'il
to
tape
type
environ
in
10 puissance
correctly
4000
one page
signes.
of Shakespeare,
Vous voyez,
you'd have to
dans
wait
l'univers tout entier,
10 to the
le nombre le
4000.
plus grand qu'on puisse imaginer,
So
c'est
the
10 puissance
huge
150.
number, the
Donc, 10
biggest
puissance
number
150
possible
à
that
l'autre-
we
à
know
côté de
about
10
the age of the
puissance
universe is
4000,
10 to the
c'est absolument rien du tout, c'est
150th,
complètement
but
insignifiant.
10 to
C'est-à-dire,
the
donc,
4000
dire
is
qu'il faudrait
even
plus longtemps que l'âge de
incredibly
l'univers
more.
pour voir les œuvres complètes de Shakespeare, ça n'a absolument aucun sens.
So it has no
C'est pas juste qu'il
sense,
faudrait
no
plus
meaning
longtemps,
at
il
all
faudrait
to say that you'd have to
inimaginablement
wait
plus longtemps.
as long as the age of the universe to
Donc,
see
tout
this
ça
monkey
juste
type
pour vous
in
donner
Shakespeare's
une
words.
idée
That doesn't even
de la
begin to
taille
describe it.
énorme.
This gives you an idea
des
of the
nombres que n'obtient,
huge size of
Quand on
numbers
commence à regarder les
that you
exponentiels.
can
Donc, le nombre
reach
des
if
puissances de
you
10,
work
on
with
commence à prendre des puissances grandes
powers
de
of
10,
10.
les nombres qu'on obtient deviennent
The numbers you
absolument
can
inimaginables.
reach
Donc, à
are
toute fin d'utile, ils
absolutely
deviennent infinis.
inimaginable. And,
L'autre chose qu'on qu'on voit dans cette
for all
dans cette
practical
vidéo,
purposes, actually infinite.
c'est que le
The other
comportement des
thing
lois
that
de
you
la
can
nature
see,
change
thanks to this
lorsqu'on
video,
change
is
l'échelle.
that the behavior of
Et ce qu'on
nature
voyait dans
is
cette vidéo,
different
on
if you
voit
change the scale you're
l'échelle
looking at it.
atomique, l'échelle humaine, l'échelle
If you
des
see
planètes,
the scale of atoms, of the
l'univers
human
se
beings, of the
comporte très, très
universe,
différemment
well, you notice that the
à ces
universe has a
différentes
different
échelles.
behavior from
Pourtant, les lois de la nature sont
the
les mêmes.
behavior of other scales.
Donc, pour
And
illustrer
yet,
ça, prenons par exemple les lois
the
d'un
laws
fluide.
of nature are
juste
the
de
same.
l'eau.
Let's take the laws of the
Um,
fluid,
Et
water,
vous
for
avez
example.
certainement tous vu une fois,
I'm
si
sure
vous
that
allez
you've
vous
all
balader
seen
l'été en
if
étang,
you
vous
walk
voyez ces petits insectes
past
qui
a
se baladent
pond,
sur l'eau.
these
Donc
insects,
là,
which
sur
actually
sur
walk
l'écran, vous voyez
on the water.
une photo d'un de ces insectes.
This is the picture of one of such insects.
Si nous, on essaye de faire la même
If we
chose,
tried to do the same
évidemment, ça
thing,
marchera jamais.
obviously we wouldn't
peut-être des
succeed,
exceptions,
with a few exceptions maybe.
mais en général, à
But
l'échelle
in
humaine,
general, at the
l'eau se
scale of the
comporte
human
très
being,
différemment
water
de
has
ce
a
qu'elle se
very different
comporte à
behavior
l'échelle de ces
from
insectes.
its behavior and the
Et en
scale of
particulier,
such
les
insects. In
liquides ont en fait la
particular,
propriété que
liquids have
plus
a
l'échelle est
specific
petite,
property. The smaller the
plus ils paraissent
scale,
visqueux.
the more
Et vous voyez
viscous they
ici,
seem.
Si vous voyez la
This
manière
picture
dont
shows you
l'eau se
exactly
comporte
the way
sous les
water
pattes de cet
behaves
insecte, on
under
voit que c'est
the feet of
très
this
lisse.
insect.
Ça ressemble peut-être plus à du miel
This
qu'à de l'eau.
looks more like honey
L'eau à
than
l'échelle humaine, elle ressemble plutôt à
water.
ça. Elle n'est pas
Whereas
du tout lisse, on voit
at
de
the
la
scale
turbulence.
of human
dans
beings,
l'exposé
water
de
looks
l'eau,
more like this. It's much more turbulent.
Et la raison pour ça, c'est
And the
exactement
reason
les
for
mêmes
that
équations, la
is
même mathématique qui décrit l'eau à cette
astonishing
échelle.
because the equations
cette
which
échelle.
describe the behavior of
Mais les
water at
équations
these two
que
scales are
décrivent
exactly the
sont
same ones.
Des équations non linéaires.
These
Les
are,
différents
however,
termes de
non-linear
l'équation sont
equations,
importants
and the terms
à
of these
différentes
equations
échelles.
are important, but at different
Peut-être
scales.
pour illustrer ça,
To illustrate this,
prenons l'exemple juste
I
d'une
could
image.
take the example of an image.
Imaginons cette image, on peut imaginer qu'elle
You
représente
could
aussi,
imagine
par
that
exemple, les
this
lois
image
de la nature.
represents the laws of nature.
Si on prend cette image d'une théière
This teapot,
qui contient, vous voyez, pas mal de détails,
containing quite a few
je commence à
details,
zoomer.
could be zoomed in.
Vous voyez, on voit de moins en moins de détails.
And the more
Si
you
je
zoom
zoome
in,
un peu plus
the
loin,
less details you see.
ça devient vite
And,
très monotone. Si je zoome encore un peu plus,
Rapidly,
soit on se retrouve
everything
ici,
becomes
on
monotonous
voit
and you
juste
see only
une couleur
one
pleine,
color,
pas du tout intéressante.
which is not
Ou alors
really
peut-être qu'on
interesting.
peut essayer de
Or
voir
maybe
quelque
you
chose d'un peu
can
plus
try
intéressant.
and see something more interesting. You could
même
zoom
là,
here
ça devient
at
pas
the
très
interface.
intéressant
But even
parce que
then,
vraiment deux
it's
couleurs,
not
une
very
droite qui les
interesting. There are simply two colors
Pourtant, l'image est
separated by a
exactement
line.
la même.
However, the image
juste qu'on la
itself is always
regarde
the
à
same.
des échelles
It's just
différentes,
that
et
it's
quand on
being
la voit
looked
de
at
trop
at
près,
different scales. If you
moins, tous les
see it
détails ont
from too
disparu
close, all the
plus tard,
details have disappeared.
très loin en dehors de notre champ de vision.
And they're simply
Et donc,
they
à cette
simply
échelle-là,
cannot be
ils
seen
importent pas,
any
en
longer.
quelque sorte.
So at that scale, these
Par contre,
details
on a d'autres exemples d'images
do not matter
qui
any
sont
longer.
aussi faciles à
However,
décrire mathématiquement.
other
Par exemple,
images
sur une image,
which can be
euh,
easily
cette,
described in
l'image de la
mathematical
théière,
terms are more interesting.
c'est évidemment une image qui a été
This image of the
dessinée par un
teapot, of
artiste.
course, has been drawn
Mais
by
la
an
manière dont elle
artist,
est représentée
but the
dans
way
l'ordinateur,
it
c'est en
has
fait juste
been represented by
essentiellement
the
une
computer
formule
is simply a
C'est une
mathematical
formule
formula.
mathématique, peut-être relativement compliquée, mais peut-être pas si
Rather
compliquée que ça.
complicated, yes, but not that much.
L'image qu'on voit ici, c'est ce qu'on appelle
However,
l'ensemble
the
de
image
Mandelbrot,
you see here,
et aussi
Mandelbrot's
représenté par une
set,
formule
is
mathématique, en
also
fait,
the
plus
expression
simple,
of
parce que
a
c'est que
mathematical
la
equation, a simpler one actually.
Mais elle a la
But
propriété
that
que si on
image
commence à zoomer, en fait, ça reste intéressant. Par exemple, ici,
Remains
je zoome d'abord
interesting
dans cette
even
région
though
ici.
you want,
Ce que je
even
vois,
if
c'est quelque chose
you
comme ça.
zoom in.
Et on voit ici
Let me
ces,
concentrate on that part, for
ces sortes
example.
de spirales. Maintenant,
You see
je
here
zoome
that
dans
kind
une
of
de ces
spiral,
spirales.
and if you zoom
Voilà, on
in
voit cette
into
spirale.
that spiral, you
Maintenant,
can
je
see it
zoome quelque part dans le bras de la
closer,
spirale, je vois
but
quelque chose comme
somewhere
ça.
in the arm of this
je
spiral, you
peux
see
zoomer
something different,
dans une
and
de
then
ces
you can
régions.
zoom in again,
Je vois quelque chose comme ça.
And you
je
see
peux
this.
zoomer de nouveau.
and then you zoom
ces
in again,
spirales.
and you see that.
Je vois de nouveau une spirale qui ressemble un peu à
Once
ce que
again,
je
you
voyais
see a
avant.
spiral
Je
that
zoome,
looks
je
a
vois
bit
de
like the
nouveau,
previous one, and then you
ce
zoom
genre de
in
région
here,
qui
and
ressemble un peu
you
à
see
ce qu'on avait
something
avant.
differently.
Donc, ce que vous voyez dans cet exemple,
what you see with this example
là, c'est un exemple d'image
is an
qui est
image
aussi décrite
which can
par
also
une
be
formule
described or
mathématique
is
relativement
described
simple,
by a relatively simple mathematical
mais qui a des
formula,
détails à toute échelle.
but
Je peux zoomer autant
presenting
que je veux.
details that are visible at
Si
every
l'image d'origine
scale.
était de la taille d'une affiche,
If
je
the
pourrais aller
initial image
regarder à
was
l'échelle atomique, à l'échelle
big
sous-atomique,
like
et
a
on
piece of
verrait
paper,
toujours des
you could
détails.
zoom
Ça
in
ressemblerait toujours
up
plus
to
ou
the
moins à quelque
atomic
chose comme
or
ça.
subatomic scale, and you would still
Et
see
ça, c'est ce qu'on
very
appelle
interesting
une
details.
fractale.
And that
Donc,
is what you call a
c'est une
fractal.
image
A fractal
qui
is
montre des
precisely
détails
an image showing
à toute
details,
échelle.
whichever the scale is you're in.
Mais c'est intéressant aussi d'étudier des modèles
But it's also
qui
interesting to
décrivent
study models
des éléments de la
describing
réalité
elements
qui ont ce genre de
of
comportements
reality
fractaux, c'est-à-dire qui ont des comportements
having that kind
intéressants.
of fractal behavior.
échelle.
In other words, interesting behaviors,
Un
whatever the
exemple
scale.
dont j'aimerais parler un peu et dont Étienne
Let me take an
Gis avait déjà
example.
parlé lundi,
Etienne
le
Gis
système de Lorentz.
mentioned it
Donc,
already on
Lorentz,
Monday.
vous avez déjà vu
This
la
example
photo
is
de ce
Lorenz's
côté-là.
system. For those who attended the first
Écrit
conference, you
dans
know
les
what it's all about.
dans les années 60, a
Around
proposé un
1960,
modèle
Lorentz
très, très
proposed a
simplifié
very simplified
convection
model
atmosphérique.
of
Donc, c'est
atmospheric
un modèle avec
conversion
juste trois quantités
with
qui évoluent
only
au cours
three
du temps. Ces trois
quantities
quantités ici,
or
on
three
les appelle
values
X, Y et
changing
Z.
with time,
On
which
pourrait
we call
imaginer ça comme les
X,
trois
Y,
coordonnées d'un
and Z,
point dans l'espace.
just like
Donc, c'est un
the
point qui
coordinates
évolue au
of
cours du
a
temps.
point in space,
Et on a
which
ces
changes
équations
with time.
relativement
And
simples, dans le
these
sens où on
rather
peut les écrire
simple
aussi en trois lignes,
equations, which can be
qui
written in
décrivent
3
l'évolution.
lines,
Donc, ce que ça veut
describe
dire
the
ici, c'est que la
evolution. What it means
vitesse,
here is that the
la vitesse
velocity
du point
of
en un endroit
the
donné
point
par des coordonnées X, Y, Z
at a
est
certain
donnée par cette formule qui dépend
point
de
with
X,
the
Y, Z.
coordinates of x, y, z is given with
Et
this.
lorsqu'on résout
these
ces
equations.
équations, on
And
obtient
if you
quelque chose comme
solve
ça.
them,
Donc ça,
you
c'est
obtain that kind of figure.
ici, peut-être
that kind of
horizontalement,
curve.
c'est la coordonnée X, verticalement,
Horizontally,
c'est
you
la
have
coordonnée
the
Z.
x coordinate.
Et
Vertically, you've
on
got the
imagine
z
qu'on part d'un
coordinate.
point quelconque,
And if you start
et on résout ces équations.
from
Donc,
any point
la trajectoire va
and
faire
you
quelque
solve
chose
the
comme ça.
equation, the trajectory will be something
Ce
like
qu'on voit
that.
dans cette image, c'est
What
deux
you
ou
see
trois
in
de
this
ces
image
trajectoires.
is 2 or 3
Et,
of these trajectories.
Ce qu'Étienne avait déjà expliqué dans son
Etienne
exposé,
explained already in his
c'est
presentation
que
on Monday
ce système
that
de Lorentz, c'est un
this
prototype
Lorentz
de système
system
chaotique.
is a prototype of a
C'est-à-dire
chaotic
que
system.
c'est essentiellement
In other words,
impossible
Essentially, it is
de prédire
impossible to predict
le comportement des trajectoires de ce système
the
au-delà de
behavior
quelques
of these
révolutions.
trajectories beyond 2 or 3 laps.
Ici, en particulier, si, vous voyez,
In particular with this example,
l'évolution de ce système,
if you see the
c'est
evolution of this
essentiellement, on
system,
a ces deux points,
essentially you have
autour
these 2
desquels le
points
système a tendance à
around
tourner,
which the
et
system
de temps en temps, il
tends to
passe de l'un à
revolve.
l'autre.
And
Donc, on tourne
sometimes
autour d'un de
it
ces
goes
points,
from one of
ensuite
these
on
points
passe
to the
autour de
next
celui-là,
one,
on tourne autour de
starting
celui-là,
with this
ensuite on
one,
passe
then
à
going to
celui-là,
the other
etc.
one and back and forth.
Et une chose qu'on pourrait aimer prédire, c'est dans lequel
What
de ces
could be
deux lobes
predicted would be
on va se
in
retrouver après un
which
temps
one
donné, étant
of these
donné
two
qu'on est
lobes
parti d'un certain-
you'll find
d'un
yourself
certain
after a
point en temps zéro.
certain time.
Et on peut se demander quelle est la précision qu'il
And
faut
you could
au temps
wonder
zéro
what
pour prédire, pour
kind
pouvoir
of
prédire
precision
avec
you need
certitude
at time
dans
zero
lequel des
to
deux
be able
lobes
to
on se
predict
trouve au temps t.
with certainty in which one
Et
of
il
these two
s'avère que
lobes
cette
you'll
précision,
find
c'est
yourself.
environ 10 puissance moins
This precision
0,4
is about
fois
10
t. Et
to
ici,
the
les échelles
minus
de temps sont telles que le
0.4.
temps qu'il faut pour tourner autour d'un lobe,
the
c'est
time you
environ
need
1.
to go around a lobe
Donc ce que ça veut dire, c'est que
is about 1
environ
second,
toutes les deux
which means that every
secondes ou
2
toutes les deux
seconds
unités de temps,
or every 2
la
units of
précision
time,
qu'il faut pour
the
prédire dans
precision
quel
you
lobe on va
need
se
to
retrouver,
predict where you'll find yourself,
elle est multipliée d'un
in
facteur
which
10.
lobe you'll find yourself, is multiplied by a factor
En
of 10.
pratique, ça veut dire qu'on
In
peut jamais
practical terms,
prédire
you
plus
are never in a
peut-être une
position to
vingtaine
predict
de révolutions à l'avance.
More than
Parce qu'au bout d'une
20
vingtaine de
revolutions in
T égale à
advance.
20, 0,5 fois 0,4
Because
fois T, c'est déjà presque 10.
0.4
10 puissance moins
times
10,
T
ce serait
is
déjà l'échelle
10 to
atomique.
the minus 10. That would be already the atomic scale.
Et alors, évidemment, une chose qu'on aimerait en tant que
Obviously,
mathématicien ou
as
en
a
tant que
mathematician
physicien,
or as a
une
physicist,
question qu'on se pose, alors c'est
there is an
puisque c'est
interesting
impossible
question
de
to be asked.
prédire
Since
avec
it's
certitude,
impossible to predict
dans quel
with any
lobe on
kind
va
of
se retrouver,
certainty in
même si
which one of
l'équation
these two lobes you'll
d'évolution
find yourself,
est
even
complètement
if
déterministe,
the solution to the equation is totally
qu'est-ce qu'on peut quand même
deterministic,
dire sur
what
cette évolution?
can you possibly say about this
Alors,
evolution?
Étienne, lundi, a expliqué qu'on
Etienne
pouvait
explained on
prédire des
Monday
quantités
that it's
statistiques.
possible to predict
Effectivement,
statistical
on peut dire, par
quantities.
exemple,
Obviously, you can
on pourrait
indeed.
faire une statistique
You could, for
de,
example,
donc si on met ici la coordonnée
calculate
X, on a
statistics
les centres des deux lobes, ce serait deux
with
points
the
ici.
centers of these
Et
two
si on fait une
lobes,
statistique
and if you
de
calculate
l'endroit
statistics
où la
of
coordonnée
the
de X va
place
se retrouver,
where
ça va peut-être
the
ressembler
x
à quelque
coordinate
chose
will
comme ça.
find out,
Et que ça va
will be
souvent
found
se
out.
retrouver autour
You'll
de
probably get a
celui-là,
kind of curve like
soit
this,
autour de celui-là.
which means that
Et cette statistique-là,
the curve will go
elle est
around
stable, dans le
this
sens où si on regarde un
point
système
or
de
the other
différents,
point.
on se
And
retrouve
this
avec une statistique un peu
statistic
similaire.
is stable, which means that
Aujourd'hui, j'aimerais
the
discuter
curve
d'une autre
looks more or less always the same. But today I'd like
une autre
to
chose qu'on peut également
mention something
prédire
else that can
sur le
also be
comportement de ce
predicted
système
on the
au-delà
basis
de la
of such a
statistique
behavior beyond
d'une
the
définition.
statistics of that
qui est
was
la chose
mentioned earlier.
suivante. On peut interpréter, par exemple, une des
It's
coordonnées,
possible to
disons,
interpret
la première
one of these
coordonnée,
coordinates, for example,
comme
the
une
first one,
vitesse,
as
et
being
dessiner
a
la position
velocity
correspondante
and
en fonction du temps.
draw
D'accord?
the
Donc, si
position
j'interprète ça comme une vitesse, ça veut dire quoi?
as a
Ça veut dire
function of
que
time. If this is
quand je me
interpreted as
retrouve
a
ici, la
velocity,
vitesse est
it means
positive,
that
donc le
the
zéro,
velocity is positive if you are here
au
on this
milieu,
side,
c'est
and
la-
zero
l'image est
is
symétrique.
in the middle. The image is totally
quand je me
symmetric.
retrouve quelque part par là, la vitesse
When
est
you're
positive.
here, for
Quand je me
example,
retrouve
the
par ici, la
velocity is
vitesse est
positive. If
négative.
you're on the other side, the speed is
Ce que je
negative.
dessine ici,
So what I'm
c'est
drawing
le long d'une
here on this
trajectoire.
curve
Quand je me
is
retrouve à droite,
along
je
a
monte.
trajectory if I am
Quand je
at
me
the
retrouve à
right
gauche,
of the
je
curve,
redescends.
I
Donc,
go up,
j'interprète
and if I'm
la
at the
coordonnée,
left,
la première
of
coordonnée
this
spatiale
curve,
comme une vitesse,
I go down.
et je dessine.
The first coordinate is
la
therefore
position
interpreted as a spatial
correspondante. Donc, à
coordinate,
chaque fois
and
que la trajectoire se
I plot
trouve à
the
droite,
velocity.
je vais
Every
monter.
time the
À chaque fois que je
trajectory is
retrouve
on
à
the
gauche,
right,
je vais descendre, et
I'm
plus
going
elle est à
up,
droite,
and
plus
every
je
time I'm
monte
at
vite.
the left hand
Plus
side,
elle est à gauche,
I'm going
plus je
down.
descends vite. Si je suis près du centre,
If I'm close to the center,
je vais
then I probably stay
je continue
at a
horizontalement.
planar level or
Donc ce
horizontal
que je
level.
vois, c'est quelque chose comme ça.
This is then what I see.
Donc là, c'est en temps 5, c'est environ 5 révolutions.
This
Si je regarde
is
en
a
temps
plot
plus long,
after
en
5
5 ans, je vois quelque
revolutions.
chose comme ça. Donc,
But on
de
the
temps en temps,
longer
ça monte, ça
term,
monte pendant un bon bout de
I'd
temps,
probably
ensuite,
have
ça
a curve
descend,
like
ça remonte,
this.
ça descend, etc.
Going up and down, and then up
en
and
temps
down,
encore
and
plus
down
long,
again,
je vois
and up again.
des montées des
With a
descentes, ça se
longer
comporte plus ou moins ça a l'air
Time,
de se comporter de manière
it
très
seems
aléatoire.
to have a
Et
very
ici, en temps
erratic
très
or
long,
random
5000, je
behavior.
vois cette
With a time of
trajectoire
5,000,
très irrégulière, très
I see
rugueuse.
this very irregular trajectory.
Alors j'aimerais pouvoir dire quelque chose,
I'd like to be able to
sur
say
cette trajectoire.
something about this
Même
trajectory.
sans pouvoir... Vous voyez, c'est impossible de prédire avec certitude.
But you see, it's
même si je
impossible
connais
to
la
predict
condition
with
initiale
certainty,
ici, c'est impossible
even
de
if I
prédire
know the
avec
initial
certitude
condition
si
here.
je
It's
vais monter
impossible
ici
to
ou si je
predict
vais descendre,
whether
d'accord?
it's
J'aimerais
going
quand
to
même faire des
go up
prédictions
or down
sur cette
at that
trajectoire.
other point
Et
in
ce
time.
qu'on voit ici, on a l'impression
What you
que
observe
ça
there
ressemble
seems
un modèle
similar
aléatoire très très
to
simple,
a
qui
very
serait
simple
simplement le jeu de pile ou
random
face.
model, just
Donc,
like playing
imaginons, je prends
heads or
une pièce
tails.
de monnaie,
If you take a
et on
coin
lance la pièce de monnaie,
and you throw it
pile,
in the air,
je gagne
when
un
it
franc,
falls,
face, je perds un franc. Donc je pars de zéro,
if it's
et
heads,
j'imagine que je peux
I
aussi
win.
m'endetter,
If it's
pour
tails, I
avoir
lose.
un avoir négatif.
So you start with a certain amount of
et je
money and
dessine
you lose 1 franc
le
or
contenu
gain
de mon
1 franc,
porte-monnaie
as
au
the
cours du
case
temps.
may
Donc,
be.
au début,
And
je
you
pars à
can
zéro,
plot how much money you've gained or lost. So start, I'm having heads, and then I gain 1 franc, gain again, then I lose, then I gain, etc., etc. So in the end, what I get is a trajectory which seems a bit like a caricature of the trajectory which I mentioned or observed earlier on. There again, the question can be asked, what's the behavior going to look like after a great number of games? If you play that game for 3,000 times, you come up with a plot that looks very much like the one that was extracted from Lorenz's system. But maybe it's just a matter of chance. Maybe it's a matter of a coincidence. Maybe any random event is going to look like that. Well, I'm going to try and convince you that this is not a coincidence at all. These two models, at that kind of scale, are not simply looking like each other. They are the same in mathematical terms. This specific model is called Wiener's process, or Brownian movement, if you're a physicist. And historically,
d'abord étudié par Brown. En fait, Brown
studied by Brown to start with. Brown was a biologist who lived, I think, in the first half of the 19th century. And
ce qu'il a fait, c'est qu'il a regardé sous le microscope.
He looked under his microscope the behavior of pollen particles suspended in water. And he noticed that these pollen particles had a very erratic movement, even though water was completely still.
A priori, on voit pas d'influence externe sous laquelle les particules bougeraient.
Having no external influence explaining these movements. And the open question that remained open for a very long time was, is it possible to study the movement of these particles and get a good mathematical model? Einstein and Smoluchowski developed independently from each other at the beginning of the 19th century. This is on the left-hand side Einstein, and the other one is Smoluchowski, who was a teacher, professor at the University of Vienna at the time. They both developed at the beginning of the 19th century, 20th century, sorry, a theory of Brownian movement,
en deux parties. Alors d'une part, du point de vue physique, c'est que la raison pour laquelle on voit ce mouvement brownien, c'est parce que les particules de pollen entrent en collision avec les molécules d'eau. Donc imaginez-vous ces grandes particules de pollen, grandes à l'échelle des molécules d'eau. On a les molécules d'eau.
You've got these water molecules which are quite smaller next to the pollen, but everywhere. And these molecules of water move around just a bit like billiard balls. And when they collide with the pollen particle, they kind of push it in one direction. If this water molecule collides with the pollen, then the pollen will move in that direction. Then you'll have probably a collision from the other molecule, and then the pollen will move in another direction. So the theory says that the total of these collisions creates a macroscopic movement that can be observed. Another part of the theory was linked with mathematics. This movement could be described, but since it is a random movement, you can't predict it with any certainty. The only thing you can predict is a probability. And in this specific instance, what Einstein and Smoluchowski maintained was that the probability, since the pollen particle was at a certain point in time, at a certain place, the distribution of probability of where this pollen particle will be, let's say, for example, a second later. And the distribution of this probability can be described with an equation called heat equation, which describes the behavior of heat, precisely, the diffusion of heat in a solid body.
Et ça a conduit, cette théorie du mouvement brownien, ça a conduit à des prédictions
Brownian movement theory
qui ont été
enabled both researchers and others to make quantitative predictions. Particularly, Perrin was able to receive the Nobel Prize in 1908 for that. And the reason why he received the Nobel Prize for that was that he made an experimental verification of the equation, which made all the other debates completely moot. At the time, people were reluctant to accept this, but he was able to prove, very scientifically speaking, that there was no other explanation, that this was the right explanation indeed, and you could verify it experimentally.
The same Brownian movement at the same time appeared in the thesis of a young man called Bachelier, who submitted his theory on speculation at the beginning of the 20th century. Now, unfortunately for him, he wasn't extremely successful. The probabilists of the period were interested by mathematics, pure mathematics, that is. And they didn't want mathematics to be used to describe things which were very materialistic, for example, the rate of the stock exchange. So they didn't really support Bachelier. And Bachelier never really got a university position. The first position he got at university, I think it must have been in Bordeaux, and that was at the age of 57. He gave private classes before that and taught in secondary school. Now, he was interested in the stock exchange and developments in rates on the stock exchange. And he described a mechanism which could explain the evolution of rates on the stock exchange. Now, if you take, for example, the price of a share, for example, a Google share, what is going to get the price of that share to change is you're going to have people buying and selling that share. And every time somebody buys the share, the price will go up, and everybody sells, then that price will go down somewhat. When you and I buy or sell shares, there may be small amounts involved. And so the effect is going to have virtually no effect on the price of the share. It's like the collision of one molecule. The pollen will not affect the collision, but if you've got billions of molecules which are in collision with the pollen, that's going to give you a macroscopic collision. And that is the same thing for the stock exchange. If you've got hundreds of thousands of people who buy and sell shares, each of these transactions has a negligible effect per se on the rates and on the amounts of value of the stock exchange shares, but the cumulative effect is actually something that you can see. And in his thesis, you've got a mathematical explanation. It's the same description as in that of Smoluchowski and Einstein, and that established the basis for modern finance, and in particular for the work done by Black and Scholes, who in the 1970s developed their Black and Scholes formula and that was used for a put price, and they got the Nobel Prize for Economics in 1997 for that work. So what you can see here is the same mathematical theory, which is shown here by the distribution of probability given to you by the heat equation, that is to be found in completely different contexts. It's equally true for the rates on the stock exchange. It's also something that can be used to describe the Brownian effect. And intuitively, it's basically the same thing. You have a mechanism which allows the price of the stock exchange to go up or down, or to move the pollen to the left or the right. And the mechanism in question is that you're going to have a lot of small events which appear to be independent and chaotic. Each of these small events has an infinitesimally small effect, but the cumulative effect is large. And that is exactly the same thing with this game of heads or tails. If you've got 3,000 games, each individual part or each individual game will contribute very little to a final result or to the final prize that you may win. But if you look at the accumulative effect of 3,000 games of head or face, even though everything seems to be completely independent and random, in the example of the Lorentz system, intuitively, you can see the mechanism is basically the same. In other words, you've got this chaotic evolution with the two lobes, and it seems to be chaotic, where you have movement from the left to the right lobe and vice versa. And you can see that curves will go up or down, down if you're on the left-hand side, up if you're on the right-hand side. So, we have a mathematical object, which is an ideal object or idealized object, which is the Brownian movement, which provides you with a continuous random curve, and which describes the behavior of all the systems I've described on a very large scale. So you can see that all these systems on a large scale are described by exactly the same mathematical object. This mathematical object has a particular attraction. You can zoom for as much as you want. It continues to behave in a very interesting manner. You don't see just a straight line.
Et voilà, donc elle est autosimilaire dans le sens que
and it is auto-similar. So you can zoom and you'll see the same distribution. Statistically speaking, it's exactly the same curve, even though it evolves, but the statistics remain the same.
Alors, cette intuition qu'on a ici,
this intuition we have here, which is that systems which behave similarly, but not in an identical manner. But if you look at them on a larger scale, they start to behave in a very similar fashion. And that intuition was developed by Wilson. Wilson was a physician. I think he got his Nobel Prize in 1980, and in the 1960s, he developed a theory on standardization curve. And his theory was, when you speak of a mathematical theory which describes a physical object, and if you ask whether two theories are close or whether they describe similar products, now, there is no reason just to compare the two theories in order to look at the mathematical parameters of the two models. What you need to do is to fix a scale of magnitude, and you've got to be able to compare the physical predictions which are relevant at this particular scale. So, to compare mathematical models which describe the physical world, you're not just going to compare models, but you're going to compare models at a particular scale. And if you do that, you have a natural dynamics in the space of models, which is the dynamics of the change of scale, which is exactly what you saw in the video at the beginning. At the beginning, what you saw is a physical system, which was the universe in its entirety, and then you changed scale. You started to see something at the microscopic level, and then you zoomed up to the level of the universe. Wilson explains to us that it may be useful to imagine that you have a space of physical theories, which is shown in this drawing. In other words, this is a space of physical theories. You have natural dynamism, which is shown by these arrows here. And that dynamism, that is a dynamism of zooming. You're changing your scale, and even if you are looking at the same physical theory, you're looking at it with a different scale, and there it behaves differently. So this begs the question, in this space of theories, are there theories that are more interesting or more relevant than others? And more specifically, are there theories which are fixed points? In other words, it's a theory which does not change when you change scale. That is something when we looked at the Brownian movements. You had fixed points, a fixed point. You can change scale as much as you wish. You saw that video I showed you earlier on in the Brownian movement. I can change scale as much as I want, but it remains the same theory. It behaves in exactly the same manner. And so it corresponds to a fixed point in this space of mathematical theories. Now, if it is an attractive fixed point, it means to say that there are lots of other theories, and when you zoom on a larger scale, they behave like this theory on Brownian movement. And that is exactly what we saw in the different examples I showed you. If you wanted to have a mathematical description of a heads or tails game, it's quite different than when you have a mathematical description of the Lorentz theory. And it corresponds basically to two different points in this space of theory. But when you zoom up to a very large scale, when you look at the other points of the theory, the two theories have exactly the same behavior. They converge towards the same point. So that moves in the direction of a possible explanation, and of course there are many other explanations, but moves in the direction of the famous Widmer's experiment, which spoke about the unreasonable efficiency of mathematics. And the idea behind this was, how come mathematics is so efficient in describing nature? Now, that's a very profound point, which has been a subject of debate for a very long time. But this is a small element which gives a new perspective on this aspect.
Alors, maintenant, donc, tout ce que je vous ai raconté jusqu'à maintenant, le mouvement brownien, ça date.
I've spoken about Brownian movements, and this dates back to the beginning of the 20th century. The mathematical description came a bit later, but this was done in the first half of the 20th century. Now, let me show you something which is relatively similar, but which is much more recent.
Donc ça, c'est la situation des fluctuations d'interface.
This is the fluctuation of interfaces.
Imagine
you have a situation, a two-dimensional situation, when you've got two regions. You can see a forest fire here. You've got this part which is burnt, and you've got this part which isn't burnt yet. And you've got this flame area which separates the two areas. And this flame base is moving towards the right, and you can see that there are random fluctuations. It's more or less straight. You can see the basis of the fire movement, but at the same time you've got random movements shown here, which are random movements around the straight line. And what we would like to be able to do is to describe those fluctuations. Now, we've got other systems which behave in the same manner. What I'm showing you is a microscopic photograph of a liquid crystal. You can have a stable and an unstable phase, two phases, and the stable phase is separated from the other phase by this interface. Or we could take other mathematical models which represent this kind of situation. A game model would be a model, for example, with bricks, which are placed one on top of one another. And the way that this functions is that the bricks fall from the sky, and they fall, they keep falling, either until they fall on bricks that were already in place, or they will perhaps, if you had 3 or 4 bricks which had already fallen, but if you have a brick that falls to the one side, it is going to be stuck to the brick next to it. It won't fall to the bottom. So if I take this system, you have the impression that this has nothing to do with liquid crystals or forest fires, but it gives you a model where you have a region with bricks and you have an interface above it, which is the area above this set of bricks. I'm going to give you a simulation of this stack of bricks, and the stack of bricks gets bigger and bigger, and you can see this at a very large scale. And you have the bricks at the bottom, and you have a more or less straight interface, but you also have a random movement in that interface.
Dans cette situation,
in such situations,
il s'avère que on a deux
you will see there are two classes of universality. You've got two of these fixed points. One which is named after Edwards Wilkinson, which is a symmetrical class where you've got the two phases are stable and you're going to get a symmetrical movement in the two phases. And then you also have an asymmetrical system such as the one I've just shown you, where you have the two regions which are in phase.
Et alors, bon, on conjecture, donc ça, ce sont des théorèmes pour certains
These
modèles.
Are theorems for certain models. But for some of these theorems, they're just conjectures. But you look at the number of interfaces that you can describe in mathematical terms. When you look at them on a large scale, and they will converge. They will converge either towards this Edward Wilkinson or towards the KPZ asymmetrical class.
Et alors là,
There is a very recent theorem which says that the KPZ fixed point, which was imagined in the 1980s in literature on physics, that KPZ fixed point actually exists. The analogy would be the Brownian movement, which dates back to the beginning of the 20th century. In this interface fluctuation situation, what we are dealing with, and this is something that came up 3 years ago, where you can have an idealized mathematical object. And this will apply to lots of different interface models. The other question that we need to ask is that for this dynamics, there are certain models which are inserted by the symmetrical, other by the KPZ asymmetrical system. What about those systems where you're between the two, where you've got Edward Wilkinson being the prime attraction, but which are going to be more attracted by KFZ on a very large scale? So the question, is there an idealized model which would be KPZ on a large scale and Edward Wilkinson at a low scale or at a smaller scale? And the question is this unique? Is there just one, or are there several? This is a mathematical model I've worked on for some time over the last few years. And we are able to show that there is an object which is called the KPZ equation, which was described by KP and Z. This was an equation which was formulated in the 1980s. It is a stochastic partially derived equation which shows about mutations over a time-space continuum. And the solutions are very irregular. At every instant, the solutions look at a Brownian movement in space. In other words, they are self-similar, but they're very irregular, as is to be expected in the Brownian movement. Give you something like this. And they are so irregular that the slope is infinite at each place. You have this infinite point at each space. In this equation, this is the square of the slope. So if the slope is vertical, it is infinite, and then the square of the slope is infinite. So you have an equation which actually doesn't make sense, because on the right-hand side, the slope is infinite. So you've got to have an infinite constant which can be subtracted. So the theorem, it's not a single theorem. Actually, it's a group of theorems developed by a number of different persons working in cooperation with many persons. So there is a notion of solution, and the solution is stable under disruption. As you have this infinity has to be interpreted in the proper manner. You have the impression that there are several ways of interpreting this, and that you could end up with different possible solutions. Now, if this were the case, it would suggest that there are several models which link these two fixed points, but it's not actually the case. So you've got a notion of solution which is very stable.
Bon, ça c'est, vous voyez ici, on arrive déjà à des mathématiques très contemporaines.
So this is very much part of contemporary mathematics.
Ce serait vraiment le début de toute une autre histoire.
And it is the beginning of another story in the field of standardization, which is based on how you interpret models where constants want to become or tend to become infinite. But that is a completely different matter, and I won't talk about it today. And perhaps I should stop now and say thank you for your attention, and I'll take questions. Thank you. Thank you very much for that very interesting presentation. You now have an opportunity to ask all the detailed questions on these equations. You can ask questions in English or in French. Use the interface on colloque.ch, colloque.ch. I am very happy to have Eric on stage with me, who's going to participate in this discussion. I'm going to start differently this time with you, Martin, and I'll speak about you. Now, we have seen your background, and you said when you were a young boy that you wanted to do mathematics, but you did physics at university, and in fact, you also studied computer science. No. No. Okay, so let's just say that you studied mathematics and physics, but you seem to be drawn by both. So I wonder, is it physics or the observations of the physical world which nourish your mathematical reflections, or is it the mathematical object which you apply to physics, and is it that you focus on? Which is the domain which nourishes the other? The most. That's a very personal question in a way, because I think that different people would answer that question differently, and each answer would be valid. For me, I go from physics towards mathematics. What we want to understand is mathematical models. It's the mathematics that interests me. But physics is a source of inspiration and a source of intuition, I would add, as well. A source of intuition for mathematics. So personally, I like the kind of mathematics which I can represent in relatively concrete terms. So, that's mathematics which are linked either directly or indirectly with physics. Is everything a source of inspiration in physics? You're talking about coffee which is going to be spilt on the sofa as we were preparing this presentation. You can say you could tell how the stain was going to spread in the material. Can you apply that to other areas?
Je cherche l'inspiration partout, c'est pas. Oui, j'imagine. Mais
I suppose so, but
je pense, disons, pour moi, de manière générale, c'est quand même les mathématiques qui viennent avant.
It's mathematics that come first.
Donc là, ce qui m'intéresse.
So what interests me in the example that you've given me where a cup of coffee is spilt could be a cup of tea. But it would be the behavior of the local effects of these equations. These are questions which are connected with reality, because we have descriptions of the behavior of a fluid, whether it's water or air. But the final analysis, the questions that I ask, are based on a mathematical motivation.
À la BBC récemment, quand vous avez remporté le Breakthrough Prize, vous avez dit quelque chose comme si je vous cite correctement. One thing I like about maths is that it has this kind of permanence. Et puis en 2014, dans un article que j'ai écrit quand vous avez justement remporté la médaille Fields, dans la bouche de Nicolas Monod, le professeur de mathématiques à l'EPFL,
Nicolas
disait qu'il y avait chez vous
said
une sorte de recherche de la vérité absolue, de l'esthétisme pur. Et je pose aussi la question à M. Ekman, parce qu'on en parlait encore hier soir à la suite de la conférence. Il me disait,
after the conference, I talked to Mr. Ekman, and he told me that maths have something more than physics, because maths are more true than physics. Maths are true forever, which is not necessarily the case in physics. Do you have that kind of absolute truth in maths?
Je pense qu'il y a cette quête chez plus ou moins tous les mathématiciens, mais c'est vrai
que all mathematicians are looking for this perfect truth, and it's true that it's what attracted me to mathematics.
C'est exactement ce que vous dites, c'est que
as you said, precisely, in mathematics,
une fois qu'on a démontré un
once
théorème,
you've demonstrated a theorem,
évidemment que les théorèmes sont démontrés par des êtres humains et les êtres humains sont faillibles. C'est possible que la démonstration
demonstrated by human beings, and it's possible that there is a mistake in the demonstration.
En théorie, on peut en fait maintenant formaliser.
In theory, it's possible to formalize a demonstration in a way that can be verified by someone else to make sure that there is no mistake. It's not very convenient, but in theory it's feasible. Once a proof has been understood by a sufficient number of mathematicians, you can be pretty sure
on est très très proche, disons, d'une sorte de vérité absolue ou d'une certitude
absolue. Quite
absolue,
close to an absolute certainty of the validity of the proof.
Donc une fois qu'on a une preuve mathématique,
so once you have a valid mathematical proof,
plus jamais être invalidé.
It's not going to be questioned any longer.
Ne soit plus d'intérêt.
Maybe the theorem in question is then later on replaced by something more general, more elegant, more eloquent. That may happen indeed. But you'll never have the case where from one second to the next, the theorem will be completely forgotten.
Mr. Ekman, vous voulez ajouter quelque chose?
Mr. Ekman, you want to add something?
Il a bien compris.
Well, I think he understood things very well.
En ligne, est-ce qu'il y a des questions pour Martin Herrera?
Now let's turn to online questions. Do you have a question for Mr. Herrera? Yes. A question about Mandelbrot's set, which you zoomed in very elegantly. How is it possible that the simple equation can contain so much information?
Oh. Bon, ce qu'on a bien vu quelque part, c'est que
I think it was clearly shown that.
Alors effectivement, l'équation est très simple.
Indeed, the equation is quite simple. I can even write down the equation.
C'est que
what you do with the Mandelbrot set is that you
Zn plus 1 est égal à
Zn
carré
plus 1 equals Zn to the square plus a constant. Zen is a complex number. So you have a succession of numbers starting with 0, and then you write 0 to the square plus a constant, plus c to the square plus the constant, etc., etc. And the question is,
Zn soit ça va vers l'infini ou pas?
Does Zn
vous arrivez à nous montrer votre écran,
tend to the infinite or not?
Pardon.
Oh, I'm sorry, I forgot to show you my screen. I wrote things down without you seeing them.
Ok, je montre l'écran. Voilà. D'accord, donc,
there you are.
Donc on a cette itération très simple.
You have this very easy iteration.
La seule subtilité, c'est que
the only subtlety is that this number is a complex number, and therefore is represented not by a point on a line, but a point on a plane. The question is, does this succession of numbers tend to the infinite or not? Well, it depends on the value of C.
L'ensemble des valeurs
Mandelbrot's set is the whole set of values of C such as Zn does not tend towards the infinite. The uncolored part of Mandelbrot set is the succession of all points where this equation tends towards the infinite. Once you are over 10, you know that you're going to tend towards the infinite. So the question is, how many iterations do you need until you reach 10? And then you color the point accordingly. This is the mathematical procedure which generates that Mandelbrot set. Well, obviously, this set has a very complicated fractal structure, but which remains self-similar. When you zoom in, you see new details appearing, but there is no new information. When you zoom in, you get the feeling that what you're seeing looks like what you've just seen before. There is a very similar structure in Mandelbrot's set at different scales. You'll always see things that look like each other. So there is, in that sense, not an infinity of pieces of information. This, I hope, contributes to answering your question. Yes, indeed. Another question. Is there a link between the various theories you've indicated and other types of work in other branches of mathematics, like Etienne Gis or Alexandre Kantonik? Are you working in different areas, or are these theories converging in a way? Are there links between all these theories? Well, yes, indeed. To give you an example, these mathematical objects, these equations with stochastic partial differential equations with KPZ points, the analysis of such equations has a lot of similarity with the analysis of field quantum theory. You could have the feeling that it is a completely different theory, which is used in physics to describe fundamental physics and particle physics. And when you try to describe the theory of quantum fields, you have exactly the same problem. You see infinite appear here and there, and you'd like to change the parameters to be able to create kind of things cancelling out each other. Even though the formulation of all these theories is very different, conceptually, they are very close to each other. The algebraic structures that you find on both areas are very similar. So I think that many things can be taken from one field and applied to the other. And that is a kind of situation that you come across very often in mathematics. When you study a mathematical system, you work in a specific area, but suddenly you come up with a question that is linked to a completely different area and requires you to import math from another area. That happens all the time. Yes, but how does it happen? I imagine that you're sitting at your desk in your office and thinking about something. How do you come to that kind of cross-pollination, if I may say so?
On se heurte à un problème et on voit que
suddenly you come across a problem.
De façon naturelle, disons,
you notice that,
une structure algébrique qui apparaît naturellement dans le...
There is an algebraic structure, for example, that comes up naturally
Et on se dit,
when you study the problem
tiens, il y avait
you're
cet
looking
exposé que j'avais vu il y a 5 ans.
And then suddenly you remember a presentation that you've attended 5 years ago where the speaker mentioned something that was quite similar. Maybe I should have a look at it. Maybe it's the same structure. And maybe I can learn something from that structure. And then you go and fetch the paper.
Ce genre de choses, c'est qu'une fois on a
that kind of situation happens very often.
Il faut, en tant que chercheur, on va toujours essayer d'être un peu au courant de ce qui se passe aussi.
You need to know and be aware of what's happening in other areas of mathematics.
Dans les autres domaines, et comme ça, quand on le voit apparaître, on le reconnaît.
When you see the problem, you recognize it. Let me go back to the issue of infinite. Oh, you wanted to make a comment? Okay.
Il me semble quand même que,
well, nevertheless,
disons, pour le public non initié, il y a quand même des
I'm saying this for the non-initiated audience. I think, nevertheless, that there are forms of mathematics that are very different from what we've been discussing this week. Number theory, for example, I haven't seen any connection distribution of prime numbers doesn't seem to be stochastic in any way. This is just what I wanted to add.
Je reviens sur les infinis.
So I wanted to come back to the notion of infinite. You mentioned your area of strongly non-linear stochastic partial differential equations. I'm not going to go into the details of all the terms of this notion, but you say that sometimes there is no solution to these equations, and sometimes you can even not really figure out what could be a solution. So isn't that a bit weird in a way? How do you manage that kind of situations?
Justement, alors c'est ce qu'on voit ici, c'est que
what can be observed here is
l'équation qu'on a envie d'écrire,
the equation you want to write is an idealized mathematical object.
Ce qu'on a vu dans cet exposé, si je reviens vers l'exemple du mouvement brownien.
Let me go back to the Brownian movement.
Si je prends le système de Lorentz,
if you take Lorentz system, at large scale, it behaves like a Brownian movement. But at smaller scales, the curve is much plain. But at larger scales, the movement of the curve is much more erratic.
Et alors, dans ces équations des partiels stochastiques,
that kind of stochastic partial differential equations,
on va d'abord étudier des équations qui sont lisses,
studying
dont les solutions
flat
sont lisses, pour lesquelles
equations
il y a
or equations where the solution is flat, where you have no problem finding a solution, and then you try to
de faire en sorte que l'échelle
change the scale
vers zéro, l'échelle à laquelle ces solutions sont lisses.
Or you bring the scale at which the solutions are flat close to zero.
Et à la limite, on va obtenir quelque chose d'idéalisé qui est plus lisse.
You'll probably get something which is idealized and is not flat any longer.
L'équation dont on est parti, elle a plus vraiment de sens.
So the equation you started with
si on arrive
has
à
lost its meaning.
Quelle que soit la procédure par laquelle on
shown that whatever the procedure you've applied,
alors on peut
you reach a certain limit, and then you can interpret that limit as a form of solution to your equation. Do you have any other questions? A last question here online, linking the beginning of your presentation with the end of your presentation. At the beginning, you showed this zooming out from atoms to the universe. At the beginning, you've got quantum physics, and at the end of the zoom, you were at the scale of the universe, and therefore in the physics of relativity. So the question is there any transition phase from quantum physics to relativity? And can this be mathematically explained?
C'est évidemment une des grandes questions de la
This is
physique théorique
obviously
moderne,
one of the major questions of modern theoretical physics. Is there a theory of everything containing both general relativity and quantum mechanics? And for the time being, such a theory doesn't exist yet. There is no good theory incorporating both general relativity and quantum mechanics. Indeed, what we would like to have would be one single theory including everything, where you could find both quantum mechanics at smaller scales and general relativity at larger scales. For the time being, nobody knows how you could reach that solution, unfortunately. But in practical terms, it's very rare that you have systems where both scales play a major part. In most systems, in most physical systems that you can study, you apply either quantum mechanics or general relativity, or none of both. In other words, classical mechanics, which is more or less in between.
Et donc, là, on n'a pas de problème, en quelque sorte.
And in that kind of situations, there is no problem. And then in some extreme cases, we would indeed like to be able to combine both theories. It's possible to do that on an ad hoc basis, but for the time being, we don't have any general theory, including everything.
J'ai une question plus, disons, pratique.
I have a more
Vous avez parlé de l'utilisation
You've mentioned using
des moyens informatiques pour vérifier des théories.
To verify theories.
Mais avant-hier ou la semaine passée,
the day before yesterday or last week, I read a paper in the MIT review saying that artificial intelligence had been used to solve problems. Maybe that may sound weird to you, but in our 21st century, with the computation performance of computers and artificial intelligence, do you think that it may help you imagine new solutions? Or new equations or new theories? Well, not really for the time being. For example, the article you mentioned.
Quand on parle, déjà, intelligence artificielle, c'est un peu.
Artificial intelligence is a word that you could really question. There is hardly any intelligence behind that. It's just an algorithm. But in this specific case, it's an algorithm to solve equations or stochastic partial differential equations. There are algorithms to solve these equations, but they tend to be very expensive in terms of calculation or computation time. If you want to calculate the solution of differential equations at large scales with meteorological simulations, for example, that would cost you a lot of time, of computer time. So you always want to look for ways to improve these algorithms and obtain solutions more rapidly. This is the case of people in Caltech, who led them were inspired by artificial intelligence models, creating algorithms that help solving differential equations without knowing to understand, without having to understand what the equation actually means. So you give the algorithm many different pieces of information, but and then the algorithm is going to learn in a way how to solve the equation. And once the algorithm is sufficiently trained, it can be very fast. But it's rather a question of engineering. The problem of such algorithms is that
on n'a pas vraiment de preuve qu'ils font ce qu'ils sont censés faire.
There is hardly any evidence that these algorithms work the way they are supposed to. there is no mathematical proof saying that under such and such a circumstance you can guarantee that the algorithm has certain precision. This is one of the major problems with artificial intelligence. It's very difficult to analyze what's happening really behind the scenes. It works, but it's very difficult to guarantee that it's going to work next time. And it doesn't really have much to do with a demonstration of a theorem. That kind of, in inverted commas, intelligence that was mentioned in this paper is just unable to demonstrate a theorem or even to conjecture a theorem. It's an engineering tool to solve equations in an approximate way faster. I'd like to ask you a final question about the Fields Medal and the Breakthrough Prize. Does that give you a specific status? Do you find you're a kind of an ambassador for mathematics? Does that give you a kind of feeling of responsibility? Do you think that you're supposed to talk about mathematics or not at all? Yes, obviously.
Est-ce qu'on vous demande de le faire
necessarily
fréquemment, plus souvent?
Are you asked to do that more often? Well, yes, indeed. Once you have been a laureate of that kind of prestigious prize, media come to see you and you have to talk to the general public more than to specialists. And I like to do that, so it doesn't bother me at all. I don't mind. I have no problem being an ambassador for mathematics.
C'est vrai que bon, ça donne, de ce point de vue, ça donne une certaine responsabilité.
From that point of view, obviously you have a certain responsibility.
Dans la communauté mathématique,
in the community of mathematicians,
sur le moment, ça donne une sorte de statut spécial, mais ensuite,
you certainly get a special status when you receive the medal, but later on,
on est un membre de cette communauté comme un autre.
Doesn't change much. You remain a member of that community just like the other ones, and the relationship with other mathematicians don't change. As far as the newcomers, the new generation of mathematicians are concerned, does that change anything? Well, I hope I'm going to help, indeed, yes. There is another problem with mathematics. Certain prizes are endowed with huge sums of money. Is that a kind of motivation for you?
Je pense pas que ce soit une motivation
no, I don't
directe,
think it is a direct motivation.
Si on était motivé par l'argent,
if you were motivated by money, you wouldn't probably study maths. There is a saying in mathematics that there are many other ways of earning $1 million than solving equations. Do you have another question online?
Qu'est-ce qui vous a le plus marqué lors de vos études de mathématiques?
By what were you most influenced when you studied mathematics in Geneva? On Monday, Etienne Guis showed us the Lorentz attractor. You did so too. Why didn't you choose really that type of studies? Is it being linked to the studies in Geneva? Is it a kind of inspiration? Who were you inspired by?
Bon, évidemment que Jean-Pierre m'a beaucoup.
Obviously, Jean-Pierre was a great source of influence on me when I studied in Geneva. I think I learned a lot from him and from his approach, his way of looking at mathematics, the fact that he considered it as a kind of game and not as a science.
Et je pense que, donc, évidemment, on a tous des trajectoires différentes, donc on peut.
We all have different trajectories, of course. Personally, I started reading physics at the university, and then I came back to mathematics, and my PhD obviously was officially about physics, but to be quite honest, it was a PhD on math, even though
Jean-Pierre préfère se considérer comme un physicien, mais
considers himself as a physicist.
Beaucoup d'endroits serait quand même plutôt considéré comme un mathématicien.
He's actually more of a mathematician.
Oui, je pense que ce qui m'a le plus marqué, c'est évidemment le temps que j'ai passé.
What I was most influenced by was the time I spent with Jean-Pierre discussing with him and with his other students.
Et, je pense que c'est ça qui a vraiment le plus marqué mon point de vue de la science.
This influenced my point of view and my view on science.
Vous avez envie de dire aujourd'hui à votre
Mr. Ekman,
quel message
what would you like to tell your former student? What is your message to him?
Je peux dire pour le public
well, for the general public who doesn't know that, I must say that being a student with me meant that you had to come with me and take a coffee every day at 9 and at 3 in the afternoon.
Enough.
J'ai une dernière question sur la médaille Fields, peut-être.
Last question on
les médailles Fields.
Il y a 4 grosses communautés
des pays qui
or rather,
on sait qu'ils ont beaucoup
de
lauréats. Hein. C'est la France, les États-Unis, l'Angleterre et la Russie.
the United Kingdom and Russia have the
greatest
number of
voilà, il y a des
Fields
nids de mathématiciens où on sait que voilà, de
laureates.
va naître,
how do we know where the next laureate is going to come from? How can you explain that?
Je pense, oui, alors il y a des écoles.
Yes, indeed, there are kind of schools.
Ça joue certainement un rôle.
And that certainly plays a part.
Après, bon, les pays en question, c'est aussi.
But the countries you named
le nombre de
are also, if you take the number of mathematicians, the countries where you find a great many mathematicians and the great portion of the mathematicians community.
Les universités dans ces pays
Universities in these countries have a very good reputation indeed and very often go there to study. So that is the explanation.
On arrive à la fin de cette soirée.
I think we're coming close to the end of this evening. I suppose that you've watched the first two speakers. I have a question about the origin of mathematics. Is it a creation of the spirit or a description of mathematics? Do you invent mathematics or do you construct them?
Pour moi, c'est vraiment un peu des deux.
For me, the answer is a little bit of both. I'm not sure that a distinction should be made between the two. It's just like a composer,
un compositeur écrit une pièce de musique.
When he writes a piece of music,
bon, la pièce de musique, maintenant, une fois qu'il l'a écrite,
that music, once it has been written, it exists and could be interpreted differently and played differently, could be studied.
Mais d'un autre côté,
but on the other hand,
vient quand même de l'esprit de
it comes from the mind of that creator. Mathematical objects are being created indeed, but once they're created, they exist. And other people can study them, can play with them, can look at them
de tous les points de vue, de tous les angles,
from all angles.
Etc. Donc, pour moi, quelque part, il n'y a pas vraiment.
So for me, there is no contradiction between the two. Mr. Ekman, what do you think about that? No.
D'accord, vous laissez le mot de la fin, Martin.
So that would be the last word for this evening. Thank you very much. Thank you for the discussion. And this is the end of the meeting. Tomorrow, Alain Cohn and Sarah Samandada from ID News will replace me. To conclude this evening, as usual, I want to thank you all for attending this evening. Thanks to the Wright Foundation, to Mr. Courvoisier for having organized this colloquium. Thanks to the University of Geneva for welcoming us here. Thanks to the interpreters who worked into English. And thanks to everybody who helped preparing this evening. Tomorrow, Anacon, and on Friday, the last conference should be online or on the screen with Stanislav Smirnov from the Geneva University. Last thing, there should be a sound and light show at the Parc des Bastions, but it has been postponed to 2021,
qui vous seront indiqués plus tard.
And the dates will be communicated later on.
Exposition qui s'appelle BelMath.
An exhibition BelMath was supposed to take place and here in the university, but it's been transposed online. You can watch it and see it.
Voilà.
On the website of the colloquium. I'm looking forward to find you all back for the next conferences, and take care and have a nice evening.